All right, so take a minute and set up your page. This is Unit 11 Gases, and this is for Honors Chemistry. So Unit 11 on gases. Get a straight edge, set up your paper. We're going to take the Cornell notes here. And we're going to start with strand 9. So as always, we're going to write the strand one time. So up here at the top, we've got strand 9. And strand 9, again, is all about gases. You're going to understand the principles of ideal gas behavior. And when we say an ideal gas, pretty much that's exactly what it's trying to describe. You know, when we deal with gases, this is in a perfect world where we have unicorns and puppies everywhere. What is the gas gonna be like? So you're gonna understand the principles of an ideal gas behavior, the kinetic molecular theory, KMT, we've talked about this before, and the conditions that influence the behavior of gases. So it's, again, all about gases. And we have two teks here, 9A and 9B, so it's not going to be that massive a set of notes here. And we're going to start with 9B. And 9B says that you're going to describe the postulates of the kinetic molecular theory. Okay, postulates is just a spiffy word for statements or things that they think are true here. And I'm going to write KMT I'm going to write it out one time. It's kinetic molecular theory. We've talked about this before. You guys need to dredge back in your memory and bring it up to the fore here. So the KMT, kinetic molecular theory, what we've discussed before is the kinetic molecular theory when it deals with any substance, solid, liquid, gas, it doesn't matter. And it's basically the statement that says the particles are in constant motion. Whether you're talking about molecules or atoms, particles are in constant motion. And if you heat the particles up, they speed up. If you cool them down, they slow down. Is that ringing a bell for you guys? So if it's a solid, the particles are vibrating against each other. If it's a liquid, they slide around each other, and if it's a gas, they're ricocheting off each other and going every which way. So we've talked about that kinetic molecular theory in those terms. What we're going to deal with now, though, is we're going to focus it and discuss it in terms of an ideal gas behavior. So the rest of the notes on this page are going to deal with ideal gas. So ideal gases. Ooh, you could draw a cloud around it. Gas cloud, get it? Huh? Yeah. Okay, so, and there are these postulates. These are the parts to the ideal gas law. So this is saying this is what not the ideal gas law, I'm sorry. This is what the kinetic molecular theory says. So the first thing it says is that gases are made of really small particles. Hello, we know that one already. Gases are made of really small particles. So that's a no-brainer. Yeah, they're really small particles, okay? Remember, it's not like a solid where you can crush it into smaller pieces, but they're usually kind of held together with intermolecular forces. There's something that's holding them together and more than just one individual atom or one individual molecule. So what they're saying with gases is that they're moving so quickly, you've heated them up so much that they have pulled apart from each other. So they're in individual molecules or individual atoms, just depending upon what substance you're talking about. Second, the volume of each particle is nothing when compared to the distance between the particles. The volume of each particle is like nothing, and I'm going to put nothing in quotation marks. We know the volume is there. It's not an empty space here. We know the volume is there, but basically, when you talk about things being in ideal gas form, if we say, oh, the volume of the individual atoms is so small, we can ignore it. So in our calculations, we don't have to take the volume of the individual particles into account. So the volume of each particle is nothing when compared to the distance between the particles. So we can ignore the volume of each particle. That means our calculations are going to be a whole lot simpler. Okay, so again, we're going to make some calculations with this stuff. We're going to try and figure out, well, what's going on? What's the pressure? What's the volume? What's the temperature? And so on. So we're going to use these to do some calculations. And the easier, the less complicated the calculation is, the easier it is and the more common it is that we'll be able to do these things. The third postulate says that the particles are in constant random motion and are colliding with each other. Okay, that's nothing new again. Particles are in constant random motion, so the little atoms or molecules are just constantly moving around. They hit each other. And they're colliding not only with each other, but also with the walls of the container. Okay, so when I say the walls of the container, if we're not, we don't think necessarily of ourselves or our room being the container. We think container and we think small, and that's not necessarily so. So expand your ideas of what a container is. So they're going to be hitting each other, and they're going to be hitting the walls of the container, and this produces pressure. So if you remember, when you think about gases, they can change volume, they can change pressure. So that's something that's constantly changing. Just, you modify one and you get a different one. So exactly let me move that up some. Exactly what is pressure? Well, pressure is caused by the particles hitting the sides of the container. Now, I bring the whole thing about the container to fore because you have right now, if you think about where you're sitting now, you have about 14 pounds per square inch of pressure hitting you all over. It's equally all over. That's just the air, the atmosphere that's rising above you. So you are considered part of the container. We think of our atmosphere, think of the whole Earth, the gravitational pull that brings the atmosphere in. Think of the outer boundary of that as the outside of our container. But our container has stuff inside of it that also has pressure on it too. So when we talk about pressure, pressure is equal to force per unit area. Okay? The fourth postulate of the kinetic molecular theory. Okay, I'm going to have to do something here and try to figure out how to do this. Give me a minute because, yeah. The fourth postulate says that gas particles don't attract or repel each other. If it's an ideal gas, the gas particles don't attract or repel each other. Think about that. If we have water, water's polar, right? So one water molecule is attracted to another water molecule. But the minute you put that water into a gas form, you no longer have to deal with water being polar in an ideal gas form because there is no attraction. They're moving so fast past each other that there's no chance for an attraction to occur. It's like if you were trying to grab someone's hand, if they were driving in a car and you were standing on the side of the road and you were going to try and grab someone's hand as they went by going 50 miles an hour, that would be almost impossible, right? So that's what they're saying. They're moving so fast that those intermolecular forces, those attractions between molecules, have no effect at all. So gas particles don't attract or repel each other. So I'm going to put in parentheses, no IMFs. We've talked a little bit about IMFs before. Those are intermolecular forces. And what this means too is that you have elastic collisions. And you'll talk about this more in physics next year. Elastic collisions. What that means is when you have elastic collisions, that the kinetic energy is perfectly transferred from one molecule to another. Okay, I don't have you guys telling me, hey, I can't see anymore, so it's kind of difficult for me. Okay, so focusing on this, that means there's no loss of energy just by hitting each other. Okay, so let's say that you had a bouncy ball and you dropped it, and you notice you drop it and then just watch it, and it'll bounce back up, but then the bounce will get lower and lower and lower. It won't bounce as high each time as if you let it sit there, and ultimately it's going to come to a stop, right? That's because every time it hits the floor, it loses a little bit of its energy. It's not a perfectly elastic collision. If it were perfectly elastic, when you drop the bouncy ball, it would come right back up exactly where you dropped it from, and it would do that over and over and over again until you stopped it from moving. Well, in an ideal gas, what they're saying is when those particles hit each other, there is no loss of energy. It's perfectly elastic. So when the gas molecules hit each other, they don't lose energy. So they just keep moving and moving and moving and moving and moving. It doesn't stop here at all. So there's no loss of energy here at all. And then postulate number 5, the average kinetic energy is proportional to the Kelvin temperature. Okay, all this year we've been dealing with Celsius in our temperature ranges. Now what we're going to do is we're going to tap into the Kelvin temperature scale. And Kelvin is basically the Celsius temperature scale dropped down 273 degrees. So the Kelvin temperature scale, the reason we use this is because there are no negative numbers. You guys have heard of absolute zero? Absolute zero is the temperature at which all motion stops. Well, that's in that Kelvin scale, and that's our absolute zero. You know, if we were in Celsius, it would be like, negative 273 point something or other. But in the Kelvin scale, when we say zero, that's as low as you can go. Okay? So in the Kelvin scale, the reason we do this, and when we do our calculations, everything, all the temperatures have to be in Kelvin. There are no negative numbers. So when we talk about our Kelvin scale, that's why it's so useful. Now, the whole thing with absolute zero. Absolute zero is the temperature at which all motion stops. All the motion stops. And that's, we talked about that vibration, even that motion stops. That's what they're saying here. All the motion stops. And the whole process or theory behind it is that we will never be able to reach absolute zero. Now, they've gotten close within, it's less than 1 degree from it, but they can't get to the point where every little bit of motion stops and that's it. Okay, I'm going to stop right here. And again, when we go through this, all we're doing is talking about the postulates of the ideal gas law, or the kinetic molecular theory when it's talking about the ideal gas law. Gases are made of really small particles. The volume of each particle is basically, we can ignore it. It's like nothing compared to how far they are apart, so we can ignore the volume. The particles are in constant random motion. They're colliding with each other in perfectly elastic collisions, and they hit the sides of the container too, and that's what causes pressure. That's 3 and 4. And then the average kinetic energy is proportional to the Kelvin temperature. So whenever we do our calculations and we use the ideal gas law, our temperature needs to be in Kelvin.